Hello and welcome back to this series of videos about the crazy electronics projects I've been working on. This Proteus design tool is able to happily simulate very complex schematics, including all of the discrete TTL logic ICs that you can see here and here, for example. If I want to simulate this, however, and actually see visual results, it is quite slow because it's relatively complex to do a fully accurate TTL simulation. The simulation from the Proteus design tool actually incorporates all sorts of latency due to all of the individual logic gates. So while it's accurate, it's also quite slow. As we'll see here, this is a virtual output display. It takes digital RGB as input and also H-sync and V-sync as input signals, and then it will rasterize, hopefully, what we want to see. And as you can see, the rasterization is pretty darn slow. So we need a better solution if we want to have meaningful software development with interactive software. And this is where emulation comes in. So let's close Proteus and we go to the emulation. Now, the emulation I have integrated with my BDD 6502 testing framework, which allows 6502 code to be created and then functionally tested using a behavioral description language. In this case, it's functional behavior, and this test case, or this test scenario, allows the hardware setup to be described in terms of what hardware layers are being created and where those hardware layers map in terms of the memory address and also the extended memory address. It also allows me to inject binary data from files into various memory addresses. It also allows me to load program files that have been assembled either by the test scenario itself or offline from a batch file or something like that, or a make file, for example. And then it allows me to start executing this assembled code. This code, these PRG files, are actually loadable and executable by Commodore 64 emulators and actually the real Commodore 64 itself. And if you've watched my other videos, you've seen me run similar program files to actually get the real hardware up and running. In the emulation, all I have to do is just start one of the build files, and this is the emulated video output. This is actually one of the standard demonstrations, part of the video hardware SDK. It includes audio emulation as well, as you can probably hear in the background, and the assets being used are from a game called Shadow of the Beast. I'm using this to demonstrate and to also test out the functionality primarily of the APU, which is an advanced processing unit, which is like a co-processor, if you like. It runs in parallel with the main CPU found inside the Commodore 64, but its sole purpose is to wait for specific positions on the horizontal and vertical position on the screen, and then to, as quickly as possible, update the external memory in the video or audio hardware. So this demonstration, say for example, it waits for the different positions in the horizontal off-screen positions, and then it updates the palette as it goes down the screen, creating this graduated sky fill effect. It also allows the horizontal screen positions to be updated at various different positions to create this parallax cloud effect. Now the emulation is running a little bit slower than normal because I'm recording this on my PC. Now, because this is an emulator, I can connect to it using a remote debugger. This remote debugger, when it starts, causes a breakpoint to be hit, so that's why the emulated screen has stopped. If I hit go, it will start again. If I hit break, and I'm in 6502 mode, then we can see actually that we're looking at 6502 code. Now, this specific part of the code here is updating actually into the APU bytes from the Commodore 64's memory that it's been calculating into the APU's data memory. And in this case, if I step out, it's just been finishing the execution for update tree. The next thing it's going to do on this frame is that it's going to execute the music poll function, and if I step in, we can see here it's started executing music poll. If the music is playing, and it waits until a certain time before playing the next note. If there's no next note for this frame, then all it does is that it increments the current frame time. And then what it does is that it calls these functions here, which then update the pre-calculated value for the scrolls, and then the blimps, and then the tree. The movement calculation is done after everything else because this is calculated into the Commodore 64's main RAM. And if I click on this button here, we can see from the point of view of the video hardware where it is in terms of the scan down the screen. Remember, all of the screens, all of the displays basically work on the principle of a raster scanning across, and then down scanning across, and then down the next line scanning across. And depending on the resolution of the screen, it will scan faster horizontally and it will scan faster vertically. This is how the video, pretty much all of the video displays work. If they're working off a raster, kind of like a video TV standard, which is what this hardware does. Anyway, so the blimps, the tree, the scroll positions are all calculated while the screen is drawing, but they're calculated into the Commodore 64's memory. And then if I keep on stepping over, then by the time the Commodore 64 has finished calculating everything, its CPU is usually down at this point in the frame. But the APU has been working in the background to take all of the pre-calculated values from the previous frame that are in the APU's data memory, and then it has already been working on constructing the frame in the background in terms of the tree, which is multiplexed sprites, and the blimps and the moon, and there's another blimp as well somewhere, probably off the screen here or here, and all of those are sprites too. The graduated sky fill effect is actually updating the palette using the APU to update the palette contents as it goes down the screen. We can see this if we switch to the APU. We can see actually, well, so going back, the main loop game will then go back to the main loop here, and then the Commodore 64 will do a wait for the next VBlank. So while the Commodore 64 is waiting for a VBlank here, that's going to be a busy wait. We're not really going to be interested in that. We can step in and we can see what the Commodore 64 code does. It's going to be waiting for the interrupt control signal to be asserted by the user port, which signals a VSync or a VBlank from the video hardware. So this will go around in a very tight loop, just doing this all of the time. We're not really interested in that now. What we're interested in is what the APU is doing. So while the register debug view here will show what the Commodore 64-6502 is doing, this APU debug is going to contain, or it does contain, all of the status for the internal registers and the internal state for the APU, which is the video and audio coprocessor. And the APU code is doing this. At the moment, it's loading values for a wait instruction here, and then this is loading the values here for the wait values where we want to get to on the next screen position. So we can see at the moment that we are at vertical position 94 in hex, which is around about here, of course. And we are in the horizontal position of CE, or 0 CE. This is low byte, high byte. This is the current position. This is the position that we want to wait to. So if we step in when we're running the APU code here, then we can see that the next instruction has just been executed in this block of instructions here. And now we are at raster position 96 in hex. And we are at 166, which is about 6 pixels after 160. And this is not a surprise because the APU, although it's clocked at about 6 megahertz, it still takes a few pixel cycles to execute each instruction. This is a lot faster though than the Commodore 64's processor, which is only clocked at 1 megahertz or slightly less than 1 megahertz, and takes a significant number of pixels to execute an instruction. So the APU, being a lot faster, is able to transfer a lot more memory to the video or the audio hardware over the 24-bit bus. And because all of the video and audio registers are mapped onto this 24-bit address bus, the APU is able to perform all of these extra video and audio hardware writes as it goes down the screen. So in this case, what we're seeing here is that we're trying to load the external address value, low and high, from whatever is in the APU's internal memory. And we can see what is inside the APU's internal memory using the memory view here. Now this internal memory view here will load from, at the moment, this address value, which is 1C7, and 1C7 on the APU is around about here, which is 9609C. Here we are, 9609C. So, and the debug view actually shows the memory which is going to be loaded anyway. The APU actually has two internal address values which it can select and then map into the APU's internal data RAM. We can also select the value from the internal RAM from the two different address values, or we can select the output from each of these 5 registers. We can select the output optionally from an add of these 2 register values added together, for example. And then this selected value can then optionally be written back into the internal APU data memory or the external 24-bit address bus. We can also use the value of the selected value to do an instruction skip check if we want to, so that if the value is non-zero or 0 or whatever, then the instruction can be skipped, which is useful for conditional looping, very simple conditional looping within the APU code itself. If I click on the disassembly view here, we can see that each APU's instruction is actually 4 bytes in size. This is 32 bits. This is because the instructions don't go through any kind of internal instruction decoder. The bits actually are triggering individual parts of the APU directly. So if we look at the APU's instruction set, we have lots of different operations that can be triggered by setting the relevant bit out of the 32 bits which are available for the instruction set. So in theory, it would be possible to execute several different operations in parallel, and this is what the APU allows you to do, is that it allows you to parallelize very simple operations on memory or register loading. The only point where we do not have that is the internal data select, which is actually based off just one value, which is a 3-bit value, so giving us 8 different combinations for where we want to select the internal data bus from. This allows us to build quite complex APU code to initialize various internal registers and then processing or copying at different raster positions different 16-bit or 8-bit values onto the external address bus. If I go back into the APU code, what we can see here is that if I step in, the APU is loading from the external address bus a value, and then the value, say in this example 7B, will be written to the external address bus using the currently selected external address bus values of the extended address bus 1 and the 16-bit address value of 9C00. 9C00, if we look in the documentation, is the start of the palette. So we know that the APU at this particular position on the screen, right here, where the grey area starts, where it hasn't rendered this current frame yet, we know that it's actually starting to write or copy 2 8-bit values, 2 bytes as a word, into the palette. Each palette entry is 2 bytes in size because it's 15 bits of color. So if I keep on stepping here, we can see that it's done a palette write for this position here, and then when it starts to render this next scan line, and what I can do now is that I can switch back to 6502 mode. I can do a little step in, and you'll notice that the Commodore 64's CPU takes a good chunk of pixels to execute. There we go. And if you can just about see that here, the new palette entry for the sky has just started rendering here behind this mountain. If I keep on stepping, you can see that it's starting to render a new palette entry for that particular portion of the sky. And if I keep on stepping in CPU cycles, then Commodore 64 CPU cycles, then you can see that the new palette entry for the sky is definitely rendering. If I go back to the APU and then click step in, we can see that we're starting to load a new external address value from the internal APU data memory. The APU has an instruction memory and a separate data memory. So when we look at the APU code, we define all of the instructions first, sequentially, that it goes through. And then down here, we define all of the data memory, which the APU usually sequentially accesses this too, although it's possible to have random memory access for the internal APU data memory if we so wish by resetting the internal address data pointers or loading new internal address data pointers. But usually, because we want to optimize the whole process of copying memory internally to the video or audio hardware, we have the memory organized sequentially in the APU's data memory. And we have different information depending on what we're storing. We can store, for example, the scroll values, the characters, a palette change, for example. So we need to make sure that the data layout is in synchronization with the code. So we need to make sure that the code is expecting to read the correct 16 bits of value or 3 bytes or whatever. So that's what the APU does, is that it does very fast copying at different screen positions. And if we keep on stepping in here, we can see that it's just doing another load wait. We'll try and get to somewhere a little bit more interesting. So that was also doing a palette switch. Here, what we're doing is that we're actually processing a sprite strip. So this tree in the background here is made up of what's called multiplexed sprites. Because we're only limited to about 24 16 by 16 pixel sprites, we would quickly run out of sprites if we wanted to just use those once. But what we can do is that we can start rendering the top of the tree using the sprites, and then by flipping over the sprites that we're using, once we've finished rendering the top of the tree, when we're down here, for example, we can start reusing those sprites, changing their position and changing their drawn definition to then start rendering the middle part of the tree. And we can keep on doing this as we go down the screen. So actually the sprites are used for first displaying the blimps. And then here, all of the sprites are then told to start rendering the tree. And it starts rendering this middle portion of the tree after it's finished rendering the top part of the tree, because the screen progresses down like this. And then we can reuse those sprite definitions. So that's what we're doing here, is that we're processing the next sprite strip. So what it does is that it loads the address, it then starts copying the sprite information. And what it does is that it does this at a particular point in the raster schedule so that it is safe. Once the sprites have been turned off, it is safe to update the definition of those sprites. And then after it's done the copy, several copies later, we'll waste a little bit of time and then we'll switch the sprites back on again. This gives the sprite hardware enough time to skip over the sprite definitions that were being updated and to not do any rendering for those, because it would come out as garbage because you're updating the positions as it's trying to render those sprites. So you switch it off and then you switch back on the sprites again so that it will update and start drawing the other sprites of those definitions that you haven't been changing for that frame. So in general, what we would do is that we would update the first 12 sprites on a particular scan line, and then on a subsequent scan line, on the next scan lines, we would update the sprites 12 to 23 instead of 0 to 11. So we would update the chunks of sprites in chunks of 12. Now, what we can do is that we can optimize this, because we want to have some other palette changing and we want to have some extra X scrolls and everything like that done. So what we can do is that we can update chunks of 4 sprites on each scan line and keep on going down the screen like that. That's basically what multiplexing is reusing the sprite definitions as we go down the screen. And so this remote debugger into the emulated video hardware is actually a very powerful tool which allows me or anybody else to precisely see what the internal state of the video and audio hardware is, because we actually can see the audio state here. This external debugger can also be used for the Vice emulator, which is the Vice Commodore 64 emulator, which, as I said, is a much better Commodore 64 emulator. I can show you that now. So if I close this and I run, for example, a previously assembled demonstration, going to be the scroller CF code title screen, which is showing some multiplex sprites and everything else like that, and playing some music. Then I will connect the debugger to this Vice remote debugging session, and we can see here that at this particular point in the screen, wherever it is, we can see, actually it's at line 0, cycle 3. We can see that we are executing this code. I can switch into the disassembly view. I can add in extra memory dump information. We can see all of the labels that's used for the code. and we can actually see the content of the memory at each of those labels as well. And we can have this mixed assembly in source code view to precisely debug the title screen code with the sprite multiplexer. I can switch off the disassembly view here, and it's a lot faster because it's not having to ask Vice for a dump of all of the things that it's executing at that particular point in time. But using this remote debugger is very useful for the emulated video hardware and also the Commodore 64 emulation using Vice. So thank you very much for watching this video about how to remote debug software that you want to write with the crazy expansion video and audio hardware I've been working on. If you like this kind of stuff, then please do like the video or subscribe to the channel or drop a comment in the comments section below.